Okay. All right. Welcome back, everyone. We're going to have a wonderful series of talks on the dark sector, and go ahead and kick it off.
Thanks.
Yeah.
Thanks, Lisa. Thanks to those who survived the last day. So I want to talk about some work that we did over the last few years with this group of people, friends and colleague. Marco Costa was actually here until this morning, and then he had to catch an earlier flight to Toronto. But he really did a lot of the heavy lifting of what I'm about to present. So we wanted to test long-range interactions, and I think it's a good idea to start from long-range interactions in the visible sector. So this wall of text is actually Galileo's writing in the 1700s. And this is, just to say that this idea that we want to test the equivalence between inertial and gravitational mass is rooted in the inception of the scientific method as we know it. And you can read it. I encourage everyone to go and do it if you haven't done it yet, to see how shocked he was that when he was swinging this pendulum, it was coming back all the time at the same rate. And one thing that you also learn is that this experiment of the Pisa Tower actually never happened. So this is actually a fake. It's fake news, okay? But so since the 1600, we went a long way with distortion balance experiment, and now we have very strong bounds on visible field forces, okay? So there is two kinds of bounds that you can have. One is on the range of this force, this m phi, and one is on the violations between two different objects. And so these are the departures from 1 over r. And of interest for this talk is going to be the difference of acceleration between two bodies. And now this was like a very long experiments that were run in the Washington group. They were awarded the Breakthrough Prize a few years ago. And now the best bound is coming from the satellite microscope. And they have in distortion balance experiment, the difference in acceleration between titanium and platinum is 1 part in 10 to minus 15. Okay, so this is one of the best measured number in all of particle physics. And so the bottom line, you already know it, is that there are no visible long-range forces, okay, that are allowed by the data. But now this is where the catch is, because for many of us, there is actually one kind of matter which is very important, and this is dark matter. And so it's natural to ask the question, the same question that we've been asking for 500 years about the visible sector to dark matter, okay? So when we write it, CDM, and we say matter, and we say this is a particle, we are implicitly assuming that the inertial and gravitational mass of dark matter is the same, but no one has told us that this is actually true, right? And so what we wanted to do was to ask ourselves the question, are order 1 violations of the equivalence principle possible? And more generally, what is the parameter space of long-range interactions in the dark sector? Because so far, people have only focused about really like collisions of dark matter with each other. So of course, we cannot put dark matter on the torsion balance and see if there is relative acceleration. So the slogan is that we want to use the universe as a scale, because the universe is a dynamical object. And so if this is filled with particles which move along different geodesics, then if you wait long enough, 14 billion years, then eventually you will find out if they have the same acceleration. And so the first day I complained that the fluid is not a model, for those of you who are here. And so we really wanted to sort of go from microphysics to macrophysics. And so we should really start from the interaction Lagrangian, which could describe such a force. One example is written here. So you have dark matter, which is the scalar, is coupled to a mediator, which is massless or very light, phi with a coupling constant cap. And so this is the diagram that you will be looking at. And so we do a filter definition for reasons which have to do with implementation. And so what happens is that you end up having an interaction Lagrangian, which looks like a mass term for dark matter. Okay, so you have a chi-squared, standard mass term, and now the mass is the bare mass plus field-dependent mass, okay? And this is the Lagrangian that you get for the scalar. And for example, one reason why we want to do this filter definition is that basically automatically all self-interactions can be neglected because they're suppressed by a larger power of this GS. So the new parameter of the model is the strength of this new force compared to gravity. So it's this GS over G Newton, and for us, it's conveniently normalized by 4 pi. So the first step is to go from this Lagrangian to the dynamics of particles, and then to fluids, and then eventually we have to put this into class. And so let's start with the particle dynamics. And here there is a very influential paper which was written by Glenys Farrar and Jim Peebles about 20 years ago, because it's not completely straightforward going from a Lagrangian to the dynamics of a single particle. In this case, it's relatively easy. So you have the Lagrangian is the same. It would be in the standard in GR, except that now the mass is inside the integral. You cannot pull it out because you're violating the equivalence principle. And so dark matter will try to extremize proper time. You take the variation, you derive the geodesic equation. And so this is the standard term, and you have the new term, which is due to the new force. You can convince yourself that this is actually the correct answer, because if you take the non-relativistic limit, you get Newton's law. X double dot is equal to minus the gradient of the gravitational potential. And then you have this extra term, which is coming from the gradient of this new force, okay? One thing which is important is that compared to gravity, typically, when you have new long-range forces, there is always this factor here, which is the variation of the mass compared to the value of the field. And that's because what's special about gravity is that it couples to energy, whereas in general, if you have a Lagrangian, you're coupling to number density. So then we have the particle dynamics. Let's go fluid. And so to go to fluid, there is many ways. You can coarse grain Boltzmann. You can use the energy momentum tensor. So in this case, I'm showing you how this is done via the energy momentum tensor. So here there is also one important difference with lambda CDM is that now, because you have a long-range interaction, like in electromagnetism, the individual T mu nu are not conserved, okay? So you really have to sum them up in order to have a conservation law. And then you define the fluid variables and you see the equation. So this is continuity equation for dark matter in the background. So rho dot plus 3h rho would be equal to 0, but now it's not 0 anymore. And so this automatically tells you that rho chi is not evolving as at the -3. And so you already expect strong signatures in the background, okay? Not even looking at perturbation, just in the background. And this is the Klein-Gordon equation for the mediator, okay? I could have written this as a fluid, but it's more compact as a Klein-Gordon. And this is another point which is important because for those of you who remember how we take the non-relativistic limit of the Feynman diagram, Minkowski, to define the new force, that is just a Yukawa. But now in an expanding universe, this is not even half of the story, because whatever it's mediating the new force has to gravitate and has to evolve. It cannot stay still, okay? So the strength of the force also varies with time. As I already said, this is the only parameter if the mass is small, and we'll get back to it later. So let's look at this first case. So the mass is much more than Hubble. So I'm mediating a new force on scales which are larger than the observable universe, or comparable to the observable universe. So let's see some phenomenology. And so this is one thing that which I've already said. And this is one really advantage that cosmology has, both CMB and large-scale structure over other endeavors for new physics, is that even if your new physics is parameterized by something small, like this beta, the strength of the new force, you wait 14 billion years, the effect becomes much larger, okay? So for example, here the evolution of dark matter from a to the -3, which would be the standard behavior, is not just beta, it's beta times a log, and this log is large, okay? So even if the new force is 5 times 10 to -3 of gravity, the effect on omega can be several %, okay? So because this log is almost a factor of 8. And the same is true for Hubble. So there is a factor of 8 improvement over the naive counting for new physics that you would get otherwise. And this already brings one consequence I'm gonna just flash very quickly, is that you can put a bound on this new force without even looking at the data. Because of this log enhancement, if this beta was 10%, we will end up having no dark matter today. The universe will be dominated by this mediator, which will overclose the universe instantaneously. Okay, so just even by the fact that we are having this conversation right now, I can tell you that this force has to be less than 10%. So this was the background, and now let's look at the fluctuations. Because this is a force that is changing the behavior of dark matter, you expect most of the changes to happen after equality. And because the recombination is close to equality, not much of the physics up to recombination changes. So RS is very similar, everything is very similar. What happens is that because I change Hubble, now the projection of those physical scales into angular scales is different. And so when you look at the ratio of the CLs in respect to lambda CDM, you see this oscillatory pattern, which is really just the fact that we have changed the distance to the CMB, okay, keeping the same values of the sun horizon. And so this tells you that the CMB is a very indirect probe of new long-range interactions. This is the power spectrum. And so for the power spectrum, the same thing happens. This is an attractive force mediated by a scalar. So it just makes things grow faster, and they grow faster over time. And so once again, with respect to the CDM, the increase in the fluctuations in the power is not just beta, but it's beta times the log. So, and this log is over the 8. And so for something like beta 2 times 10 to the minus 2, which is close to the CMB bound, as I will show you, the power spectrum is 20% different. Okay, so this is a huge effect. And there are minor changes to the BAO. We'll get to that later. So now I told you the story about linear fluctuations. So I could go and constrain this with the CMB, but this meeting and a lot of the things that we've been discussing are about spec 5. And so if I want to constrain this physics with large-scale structure, what do I have to do? We said this already. I have to go to these 5 stages of grief in developing the EFT of new physics. And so we did it for the first time. It was a massive amount of work by all the people that I was listing earlier. And so these are the equations of motion that you have to solve. Okay, so you have continuity equation for dark matter, Euler equation for dark matter, but now you have 2 fluids, really, because on large scales you have a force, and so you have to distinguish dark matter and baryons on any scale. And so you see in red all the places where new physics show up, and so we solved these equations. And so let me just tell you some highlights, because this force is mediated by something which is very light, larger than Hubble. I don't have a new spatial scale in my theory, so I can still separate space and time as I would do in lambda CDM. We have seen this a few days ago. So I can still write these ansatz, but then I have to check what is my time dependence, what is the structure of these Fs. And so the first result is that the time dependence is simple. So in principle, you could have arbitrarily complicated nth order growth factor, but it turns out that they are the linear to the n plus a small correction, which is not log enhanced. Okay, this is the crucial point. And this result is actually much more general. It's true, for example, if you have light relics. It's true if you have dark matter, dark radiation interaction. It's true in many, many, many scenarios. Then we have to look at the Fs. And now you have 2 Fs, one for the total perturbations, one for the relative fluctuations. And so you have to compute the corrections to those. So as expected, the corrections to the total fluctuations in the matter field get corrected. And now you have these complete new sets of kernels, which are in the relative fluctuations between the baryons and the dark matter, which are IR divergent, okay? And this IR divergence is true, because now you really cannot go to the elevator. You cannot put dark matter and baryons in the same elevator and remove the effect of the long mode. There are also new counter terms. So one thing which I wanted to say very quickly is that can we observe these relative fluctuations? And I want to bring this up because in many of the things, the discussion that we have, what happened? Oh, Zoom, no, it's my Zoom just disconnect himself, okay. Okay. We really think about lambda CDM all the time, and I'm here to tell you that there is more than that. For example, in this galaxy bias expansion, Matthias the first day said that he doesn't care, he cannot care less about big gamma 3. I subscribe, I cannot care less. However, if you have new physics, there are new parameters which won't be there in lambda CDM. So, for example, this bias parameter that I'm writing here, this is our baby version of Niels and Olivier and others primordial non-gaussianity bias, because this term would be 0 if you have if you didn't have any new physics. Okay, so if you go and you measure this term, then you're guaranteed that there is new physics. You don't know what it is, so this is not as strong as a statement as primordial non-gaussianities, but you know that there is new physics. And then there are things about the pole, which is very low signal to noise, so I'm not going to even bother you. So let me show you some bounds. Oh, there was a thing about the BO. I'm going to skip that. So these are the bounds. Okay, so the first two. The first 3 are actually real data, so Planck plus Boss, BO, or full shape. And you see that the bound on this beta, goes from the gray to the orange to the red, and we're really limited by the genus with the bias parameters, always. But you see that when you add DAISY and then you keep adding megamapper, the bounds improve substantially. And this is without including any lensing, any bispectrum, any cross correlation. There is really a huge parameter space which could be explored with future surveys. So in a few minutes, if I have a few, 2, okay, let me just flash what's going on with the mass larger than Hubble. And I want to mention this because this is one scenario in which something which typically you wouldn't expect, like Hubble oscillating at late times, actually happens in a very natural way. because now you're mediating this new force. And when the mass becomes larger than Hubble, now you cannot mediate the force because this guy is massive. It cannot really transmit anything. And so it wants to settle to the minimum of its potential, and so becomes a fraction of dark matter. Okay. And so you really have these nice features in Hubble, which we can strongly constrain with the data. But okay. So I'll slow it down. Okay. So, so I just want to bring this up because not only this is a massive opportunity at redshift, let's say, of a few, but it's also an opportunity at low redshift. Okay. So I think this is one strong case for having something very high density at low redshift. And because this mediator is now a part of dark matter, it suppresses growth like any ultra-Lyell axion would do. And it has a gene scale given by this number. And so what it's doing is this is massively suppressing the growth, okay? So when the mediator was lighter than Hubble, then it's always an attractive force, so increase the power. But now, as I increase the mass compared to Hubble, at some point, I'm not mediating anything, I'm just suppressing power. And so you see these huge effects, okay? And so in principle, we could do all the masses, but as I was saying, there are some masses which I cannot do because I don't have the EFT. And so we have to stop at about masses of the order 10 to the 5 Hubble, okay? So this is my summary. So we can really probe new long-range forces to the 0.1% level. And these are orders of magnitude better than any small-scale structure constraints existing in the literature. And I think this is strong, science case for something like Spec5, because now we can constrain self-interaction of dark matter already over 5 orders of magnitude. And if we expand this EFT, we could actually do it over 10 orders of magnitude down to the parsec, okay? Because we know we can just go all the way when K genes becomes larger than K nonlinear. And these bounds that I'm showing here with MegaMapper have not been optimized for this new physics. So we just took the numbers which were out there, but I think there is a lot of sort of optimizing that we can do for new physics. So this is all I have to say. Thank you very much for your attention.
Excellent. I'm going to ask the first question.
Go ahead.
Can you just say a little bit more about this optimizing, like just sort of schematically, what would be the best survey?
So, so what I would say is that I'm looking at Martin. Where is Martin? Martin is over there. Because there is always this argument, oh, I would like to have more galaxies, less sky. And then it always turns out that you need actually the opposite. But maybe here it's true that, once you go to high redshift, so just the volume is large because you're a high redshift, increasing the number density is useful because a lot of these effects, you can see it here, you could see it before, they become very degenerate with bias. So if you can leverage by spectrum cross correlations and other things which, can cancel some sample variance when you're not dominated by short noise, this is actually very helpful.
Okay, time for 1 or 2 questions.
Can you go back to the slide that talks about the matter convert to the mediator?
Which one? Sorry, the mass?
Yeah, just the energy conversion. I'm confused because you talk about like you convert dark matter energy to the mediator and convert maybe Hubble to mediator as well. Isn't that already pretty significant in the early universe?
In the early universe.
Yeah, right. Because I know you focus on later universe, but I'm wondering like if you have even more signatures in the early universe.
No, you don't, because let me show you Klein Gordon. You don't, because the effect is proportional to rho chi, and there is an A square, and so this A square is dominated by rho radiation, and so it makes this term very small before matter radiation equality. So this term dominates after matter radiation equality.
I see, because they dominantly couple to matter
instead
of radiation. Is that the logic?
Yeah, because you're coupling only to matter.
I see. Cool. Thanks.
More questions?
Hi, Emmanuel, great talk. You mentioned there's a production of ultralight particles. What's the abundance you have in mind for the model?
You mean the abundance of Of what? Sorry, I didn't get it.
Um, for let's say the red one.
Mm-hmm. So the fraction at late times is going to be around this number. So this is a few percent times this log square. So you can really end up having 30% of dark matter today being an ultralight axion. So that's why the bounds are so strong, are much stronger for the massive mediator than they are for the massless mediator.
Thank you so much.
Question? Okay, great. Ethan, thank you.
Good. All right, thank you for having me. So I'm excited to tell you about kind of our view from very small scale structure in terms of what we're excited about for testing fundamental physics. I'll be focusing on dwarf galaxies, but I actually wanted to start by giving you kind of a broad motivation for why we care about small scale. So this is a plot of the co-moving size of the Hubble horizon as a function of scale factor, which is decreasing during inflation and then increasing afterwards. And the point is that on progressively smaller scales, we probe modes, density fluctuations that exit the horizon later during inflation and re-enter the horizon earlier after inflation ends. And this gives us unique access to physics at those scales. So particularly, this is a plot that came out of the SNOMAS process, where I wanted to show just the range of dark matter models that can affect small-scale clustering. So this is a plot of the dimensionless linear matter power spectrum. And what you can see is there's a wide variety of dark matter physics, much of which we've heard about, that can affect the clustering of matter on small scales. And new surveys are going to be providing data on these scales, and it's I think, imperative to actually understand this and use this for cosmology. Just to give you a sense of the scales I'll be focusing on, I'm mainly going to talk about this transition between the faintest halos, the smallest halos that host dwarf galaxies, and those that remain completely dark. So observationally, our census of faint dwarf galaxies has improved really dramatically, even in the last decade. This is a really beautiful image made by Yao Yuan Mao, which shows basically every Milky Way mass host we know about within roughly 40 megaparsecs. So that's each circle. And then each little dot within each of these circles is a satellite galaxy. And of course, we've only detected the faintest of these satellites within the Milky Way. These are ultra-faint dwarfs. But you can see that the data is growing, particularly at larger distances outside the local volume. So in order to model these systems, we have to combine kind of high-resolution simulations of structure formation in a variety of dark matter models with an understanding of the galaxy halo connection that dictates the relationship between the luminous galaxies that we see and their dark matter halos. So very briefly on the modeling end, I just want to advertise two recent simulation efforts that were put out in the last years. So one is the Symphony suite of zoom-in simulations. Here, our goal was to scan over a very wide range of host halo masses and then run high-resolution n-body simulations to resolve their substructure with high fidelity. And so all of this data is publicly available. I encourage you, if you're interested in it, to check it out and play around with it. And particularly for the Milky Way, we've finished a new simulation suite recently. This was really excellent work led by an undergraduate, now master's student at Stanford, in which we specifically selected halos that resemble the Milky Way in great detail, beyond just the mass of the host halo, but in terms of their additional properties, like the existence of a large Magellanic Cloud. So again, these provide the sort of high fidelity predictions we need, combined with the appropriate galaxy halo connection modeling to actually interpret the data. On the galaxy halo connection modeling side, this is one example of an empirical model that we can use to parameterize the relationship between halos and the galaxies that they host. I don't expect you to take away all the details here, but the point is we can actually parameterize these theoretical uncertainties and then marginalize over them when we're fitting the data. All right, so we heard about this actually a couple days ago already in the conference. So from the current data, from our current observations of the Milky Way satellite population using dark energy survey and pan-stars, we can already place highly competitive bounds, for example, on the cutoff or potential cutoff in the linear matter power spectrum, here parameterized by the mass of thermal relic warm dark matter. So this analysis works out to a constraint of 6.5 keV on the dark matter mass And it complements other small-scale probes like the Lyman alpha forest and strong lensing by probing really distinct physical scale and obviously distinct systematics. So going beyond this, we've run now a comprehensive set of forecasts in models beyond just CDM, considering what the future data will bring. So this is one example, again, focusing on the warm dark matter particle mass in different scenarios. For example, we might be living in a CDM universe, and then we can forecast the bounds on the warm dark matter, or we can ask the question of whether satellite galaxies can be used to detect non-CDM physics. And these forecasts were quite optimistic. So we found that, for example, using 2 complete satellite galaxy populations, you could imagine all of the satellites of the Milky Way and M31, you can place a bound on warm dark matter at the level of 20 keV, which is really quite stringent and corresponds to linear matter power spectrum suppression of about 10% at a wave number of 50 inverse megaparsecs. There are degeneracies, of course, with the galaxy halo connection physics, but we are marginalizing over these, and we can actually characterize what additional data can help break those degeneracies. So moving beyond warm dark matter, we might consider in a sort of model-independent way how these tiny galaxies probe the subhalo mass function itself. And the results here are consistent with what I showed for warm dark matter. For example, 2 complete satellite populations can probe suppression of the subhalo mass function in a model-independent way at roughly the 20% level relative to CDM. Enhancement is more difficult to constrain because of these degeneracies, but again, additional data can help here. So these forecasts that I've shown were calibrated, essentially run on these CDM simulations I showed you before. In order to move beyond this and really get at the linear power spectrum itself, we're running now suites of simulations, zoom-in simulations beyond the CDM paradigm. So this is in collaboration with Rui, who spoke yesterday, and also Andrew Benson and Ferry Glusevich. And what we've done is run over 100 cosmological dark matter-only zoom-ins, scanning a very wide range of possibilities for the linear matter power spectrum, both in terms of the shape of the initial cutoff and secondary features like these dark acoustic oscillations. So just to give you a sense of the range of models that we've covered, I've thrown everything on one plot here. Again, I don't expect you to take away the details. And one point I want to emphasize is that these constraints will not only apply to scenarios where all of the dark matter is one non-CDM component. We're also covering fractional cases, for example, with mixed warm and cold dark matter. So the idea is that this really dense simulation coverage of possible initial conditions will allow us to place model-independent constraints on the linear matter power spectrum itself. And this is just a forecast of what the constraining power of the data will be. So again, this is a plot of the linear matter power spectrum, now not normalized by k cubed. And these 2 black error bars show the projected constraints from Milky Way satellites, which probe halos with solar masses around 10 to the 8 and corresponding to wave numbers, as I said, about 10 to 100 inverse megaparsecs. So for the first time, actual reconstruction, right, marginalizing over the galaxy halo connection uncertainties of the linear matter power spectrum is possible using dwarfs. The projected sensitivity of this analysis to running of the scalar spectral index complements large-scale structure. And upcoming surveys are going to be delivering the data needed to do this inference. So again, I think we have to do this work. Just to help you think about this space, roughly the minimum luminosity of a galaxy that a survey probes sets the wave number, right, of this constraint on the linear power. And the size of the error bar is a combination of the survey volume and the galaxy halo connection systematics. Obviously, at the moment, we're in the small number statistics regime, but as I said, this will change, right? So the challenge is on us modelers to understand the galaxy halo connection sufficiently well. Just to end with one specific set of predictions. So Rubin is coming, of course, and we predict that LSST will detect most of the remaining Milky Way satellites in the southern hemisphere, roughly 50 to 100 new dwarf galaxies in the south. Rubin alone can be prone to kind of false positive detections. You need better distances to these systems, and so better star-galaxy separation from Roman and Euclid will really help here. And of course, continued spectroscopic follow-up at high resolution is important to obtain the dynamical masses of these systems. And one more time, I just want to emphasize that spectroscopic surveys are already complementing this effort. There are large catalogs of redshifts of low redshift dwarf galaxies. For example, I think there's over 20,000 now from the DESI low Z effort going out to redshift 0.03. So I'll leave the conclusions up here. Happy to take questions.
Yes, thanks for the nice talk. So I'm curious, when you say galaxy halo connection systematics, what do you mean exactly? Is it just a uncertainty of the like a galaxy halo stellar mass, stellar halo mass relation, or this is something more
Yeah, so the stellar mass halo mass relation, both in terms of its slope and scatter, but you can also imagine the relationship between galaxy size and halo size, or the efficiency of disruption due to the galactic disk. All of these things are put into the model that I showed you and marginalized. So it's not just the stellar mass halo mass relation.
Okay, I see.
Ready to push? So I wanted to ask you. Okay, I need to. Okay. So, so you were showing these acoustic oscillations, right? And I agree with you that, of course, if this is an effect which is imprinted in the transfer function in the initial conditions, those models will be probed by the dwarfs, right? But for example, if those oscillations are coming from some dynamics like fuzzy dark matter, I don't think you can get away without running simulations of fuzzy dark matter dwarf systems, right?
Yep, agreed.
Like,
So
is this something which is planned planned from you guys to do?
yeah, definitely. So the idea here was to, specifically focus on reconstructing the linear power spectrum, so to only vary the initial conditions. But there are definitely efforts underway, like incorporating different dynamics into the simulation. So, we've already done this with models like SIDM, and we'll definitely expand it. Yeah.
Thanks.
Yeah.
Is there one more question? Yeah.
Yeah, thanks for the nice talk. So the model you have considered all feature suppression on matter power spectrum. I'm wondering, have you considered like enhancement on similar scales? Will the result be different, or like do you expect something new?
Yeah, definitely. So, I mean, the even in terms of the forecasts we've already done, the results are different for the enhanced models because those are more degenerate with the galaxy halo connection, which tends to kind of suppress structure on small scales. We're also planning simulations to do this. It's going to be, another effort, but it'll definitely be incorporated. Yeah.
All right, let's thank Ethan again. Okay, we'll hear from Huanggu Xiao.
All right. Sorry, I closed my slides. Let me. Okay. Thanks for having me here. Sorry for the technical delay. I know people are probably very tired now with this very fun, intense workshop. I will try to make this more entertaining and tell you some new phenomena I've been thinking about. It's going to be recurrent X novae and their cosmological constraints. This is work done with Patty Fox, who is also from Fermilab, and Neil Weiner from NYU. So before I really go into the details, I want to do some comparison between the universe we understand now and a universe with axion being our dark matter, which is one of the favorite dark matter candidates. So we know our universe, we have adiabatic fluctuations. Those fluctuations will lead to the collapse of large cell structure, roughly ratio 20. And then we have formation of galaxies. We have star formation in the cold and dense gas cloud. But when you think about the axion universe, especially if you love the post-inflation scenario, you already have enhanced small-scale structures, which will lead to formation of small-scale structures at matter radiation equality. And they're already cold in the sense that their virial velocity is very small. And they are also super dense because they form super early. So it's quite expected that these kind of scenarios for axion cosmology will lead to the formation of axion stars. And then axion stars, pretty much like our normal stars, will collapse and explode after a certain critical mass due to their attractive self-couplings. And those explosions will cause a change in omega matter. Therefore, if we have all the cosmological observations, it can actually be related to the dynamics of axion dark matter. And this is actually the real message I'm trying to deliver here. And I want you to take home with this. So And it's actually quite different from our normal star exposures. So let's think about our normal stars, right? We burn all the nuclear binding energy and eventually probably have supernovae. But it has an upper limit. So there's always a limit for your normal star burning because you conserve baryon number. So it's kind of well understood that the baryon number violation should not occur at these energy scales. So the maximum energy you can burn is pretty much at most 1% of its rest energy. And that's already huge, of course. But for the axon case, it's different because axon number is not necessarily conserved. And due to the cortex self-interaction, it's potentially constrained. And so if we look at this diagram, in dense axon clumps, I can have 3 axons coming together, and due to the cortical coupling, it will convert to 1 axion, which will be relativistic. So with this process, I can convert non-relativistic matter to relativistic radiation. And it's kind of doing the reverse effect compared to neutrinos, because neutrinos, you come from free-streaming neutrinos to be non-relativistic matter. And for axion, you convert clumpy axion dark matter to free-streaming relativistic axions. And what do I mean by axion star? I've introduced all of this, like I'm just trying to give some rough idea. They mostly don't emit light, so in that sense, they're really not stars, they're not blinking. By axion stars, I really mean they're the ground state solution of your axion field configurations. It's energetically favorable state. And they are balanced by the gravity and the kinetic pressure. So the first term I wrote down is simply the gravitational binding energy. The second term is simply the kinetic pressure, which comes from like uncertainty principle. The third term is usually not important, but it's important for during the collapse. It's from the self-interaction, which can cause instabilities. So here's the life cycle of axion stars. In the dilute branch, when you accrete more mass, the radius actually goes down. This is kind of different from the usual mass radius relation for all the other stars. This is because when you add more mass, you essentially add more gravity, and then you need more quantum pressure to balance it. And by more quantum pressure, you really mean a smaller radius. So your radius continue to grow. And at some point, your radius is so small, your density is so high that your self-interaction starts to play a role. And then you have this contraction, which is the axion star collapse. And you collapse all the way down at some point, not quite as dense as black holes, just very, very dense clumps. You start to trigger very strong nonlinear interaction, which will trigger this axionovae behavior and emit relativistic axions, and you pop this back up. And this cycle can repeat multiple times and depleting a significant fraction of matter to radiation. And the condensation or the formation of axion stars is an active ongoing research these years. And the timescale of axion star formation is kind of surprisingly well described by some semi-analytic formalism. And this is because, as I said, axion star is energetically favorable state. So as long as the relaxation timescale is the only barrier for you to form those objects. So as long as each axion waves can scatter with each other and reach thermalization, you tend to just form stars. And that's why you get this nice time, which is simply cross-section times velocity times whatever Bose enhancement factor. And for gravitational scattering, you know the cross-section, this is well understood. You could also have self-interaction, which will enhance the scattering rate and give you a smaller condensation timescale. And the growth itself is more subtle. I don't want to go to too much details of it because it's still a very active area of research. But basically, you know the mass, you know the timescale, you also know the mass. The mass is kind of determined by equating the virial velocity of the halo and the virial velocity of the star. And this is kind of some thermalization argument. You have like star evaporating into the environment and the environment or the halo condensing into the star. And initially, the power law grows. Afterwards, people kind of debate if this growth will continue or not. So I don't want to say too much about it because people are running a lot of simulations to really test these ideas. And a key observation is if stars are not taking away a significant fraction of the halo, this process, like I said, the life cycle of all the axion stars should be recurrent. And if you look at the plot I'm taking from Levkov's paper in 2016, the density actually starts to grow when the star collapses, and then it's emitting relativistic waves. So the central density goes back down, and then it starts to develop a large density peak again, and going this recurrently. And this is, oh, sorry. And this assumption has been confirmed by numerical studies, and we can use this assumption to get some cosmological constraints. So basically, this is a final plot. The message I'm trying to deliver here is the physics of axion star is very kind of unique, because on the one hand, you have star formation rate determined by gravity, self-interaction, and cosmology, which is the mini cluster formation. And the physics of the instability of axion stars is simply given by self-interaction. They're unrelated, and presumably this will give you constraint. And you can actually relate the matter conversion rate to axion parameters. And this is a very rough estimation. In the plot, I'm showing the parameter space that is currently excluded. In the blue region, you convert 10% of matter to radiation, which is obviously excluded. And then if you go to the right, the conversion rate will be smaller, and that could be the target for future searches. So basically, you can relate the matter conversion rate to axion parameters, and that's like people often ask, what a future so is good? A better measurement of omega matter? Yeah, better measurement of matter may tell us something about the axion parameters, and that's my conclusion here. And I will take questions. Thanks.
Okay, questions?
Hi, this is very interesting. Can I ask, when you were talking about axion novae, do they give away the energy in terms of the electromagnetic wave? And also, if there is this recurrent feature, and what's the kind of periodicity and also amplitude compared to maybe other background?
Great. You're asking two very difficult questions. The first thing, do they emit electromagnetic waves? And there are claims in the literature that saying they actually emit gravitational they emit electromagnetic waves because they have some parametric resonance. So it's kind of, I don't want to go into too much detail on this, but they're kind of assuming self-interaction is not important. So imagine you have two competing channels. One is emitting relativistic axions. Another is emitting photons. And the photon, if you consider naive axion model, your photon rate is usually, your photon coupling is suppressed by the fine structure constant, which is a lot, which is like 1/137. And this is a lot of suppression. So if you care about electromagnetic waves, you need to consider a more enhanced photon coupling to trigger this parametric resonance. So that's one answer. Does that answer your question? And for the other, what's the life cycle? Usually the collapse is pretty fast. So the formation is cosmological timescale, and the collapse is like macrophysics scale, maybe. And so the collapse is really fast. The emission is really fast too. It's roughly just a few thousand of axion oscillations, depending on what axion mass you're considering about. Maybe radio frequency axion masses, then what it is, gigahertz times 1,000. So it's microsecond. So the emission itself is microsecond, and it's very short. The collapse is also short, and the life cycle is dominated by the formation and the accretion. Yeah.
One more question? Can you say just a little bit more about this relationship to omega matter in terms of if I measure omega matter by this much better, how does it inform this?
Great. Actually, I just started to think about this last week. So
Excellent.
we should chat more, because
Okay.
I just realized that, like, so first, like, this is if you can it's pretty clear here, omega matter goes like 1/FA cubed, 1/MA cubed. So like if you have, say, if you measure omega matter to 0.1% or 10 times better, then your MA/FA get a better constraint. But I mean, it's really the constraining power is not growing too much, because it actually depends on higher power of FA and MA. Right. It's more like it's giving you some new signals. And I actually,
go Go ahead.
Sorry, I actually skipped a lot of discussions on the matter pulse spectrum. So this kind of models also feature enhanced matter pulse spectrum on small scales.
And does that just impact? I mean, that all happens pretty early. So everything in the late time universe.
You can see this goes like 1/1 plus Z5.
1/1 plus Z. Okay.
Yes.
Great.
So they all happen pretty late. So yes, it's good. Like, yeah.
Okay. Thanks. All right. Thank you. All right. Next talk by Melissa Joseph.
Hi, I'm a postdoc at University of Utah, so I'm going to be talking about some signatures of interacting dark sectors. So we know that lambda CDM is a very good model of the cosmological history, but we also know that if we look at sort of the fraction of the energy density in the universe, most of it is in some form of dark thing. And lambda CDM makes very few assumptions about what that dark thing is. And so hopefully with more data, we can ask sort of more questions about what exactly is what is in these dark sectors. So some possible questions we can think of is if you have some BSM particles that come into equilibrium with the neutrinos at early times, it's possible that some fraction of this 40% we're talking about could also correspond to other dark sector particles. And then if we think about the dark matter as a particle, we could also imagine that there's multiple dark matter particles, as well as interactions with the dark matter and dark radiation. And so some extensions of lambda CDM could be motivated by cosmological tensions that we already see in the data. So we've talked a little bit about this today already, but there's the H0 tension as well as tensions in large scale structure. So there's the S8 tension and then the Lyman alpha tension, both of them so far suggesting that we see suppression of the matter power spectrum at small scales. And so first starting with sort of the Hubble tension, one motivated model that we've looked at is stepped radiation. So this is interacting radiation, which we found fits the CMB better. So it's less constraining than free streaming radiation. And then one modification you could make is if in your interacting radiation, you have a massless particle as well as a light particle. And then in this case, we see that when the light particle reaches its mass, that there is a redshift slightly slower than radiation. And so we see that there's a step in ineffective. And so if this mass is in the EV scale, we can see these effects in the CMB. And so we found that adding this step helps in alleviating the H0 tension. But then when we're talking about interacting dark sectors, we can also suppose that some of this extra dark radiation also has interactions with the dark matter. And so then this can have implications for structure formation, as we've mentioned earlier today as well. So if the dark matter is interacting with the dark radiation, there will be some momentum exchange, and this can suppress the growth of perturbations at early times and lead to suppression in the matter power spectrum today at scales relevant for S8, as well as Lyman alpha. And so just to be a little more concrete, so what this looks like in the fluid equations is we have our standard dark matter fluid equations plus some extra term, which couples the dipole moments of the dark matter and the dark radiation. And the relevant parameter here is this gamma, which tells you the momentum transfer rate between the dark matter and the dark radiation. And this depends on the particular model you want to write down for the dark matter, dark radiation interaction. So I'll talk about a few models just to give an idea of what this could look like. So earlier we talked about dark matter, dark radiation interactions that are weakly interacting. So in this picture, we're thinking of all the dark matter is interacting with some dark radiation. And so these interactions will be quite weak. And then we can consider what the effect of having a mass threshold in the dark radiation is. And that effectively shuts off the interactions between the dark matter and the dark radiation. So once we reach the temperature of our scalar in this model, we find that the dark matter interactions are suppressed. And in this particular model, we get a power law suppression of the momentum exchange rate. And so Hengame showed a few of these plots earlier, but the effect of the dark matter, dark radiation here is that the interaction strength tells us the slope of the suppression. And because we're considering weakly coupled dark matter, we're always going to see a smooth suppression that's proportional to log K. And then the effect of the mass threshold, so this is the mass of our light particle in the dark radiation, tells us the scale at which the suppression of the matter power spectrum starts. And so this is a free parameter, but moving the free parameter tells you the cutoff scale in the power spectrum. So this sort of looks like running, but with like broken power law spectrum. And then the other limit we can consider is we have some dark matter that is strongly interacting with a dark radiation. And in this case, we're thinking about some fraction of the dark matter that is interacting with the radiation. And one model that you could write down for this is if you have, again, so dark matter, dark radiation. And in this model, you could have a light fermion and then mediated by a gauge boson. And so in this one, we see that the light fermion, when it reaches this mass, the dark matter particles the interactions between the dark matter will shut off. But this is given now by an exponential relation because of the fermion. The dark radiation is annihilating away. And so in this case, we see the strongly interacting dark matter, dark radiation interactions. And so here, a fraction of the dark matter is strongly interacting. And so you can see some features which look like dark acoustic oscillations in the linear matter power spectrum. Unclear if they'll remain with nonlinear corrections. But then again, the feature that we have an exponential shutoff of the dark matter, dark radiation interactions. So that looks like sort of a steep decline in the matter power spectrum at the mass threshold. And then again, we have the same feature that the mass threshold tells us when the suppression of the matter power spectrum starts. So what K scale we're looking at. And then here I just plotted, again, these three models that I've talked about with and without a step, and then the strongly and weakly interacting scale, just to show that these models all give sort of a suppression of the matter power spectrum at different scales. And the with and without a step can change the scale at which the suppression starts. But they all sort of can be degenerate at larger scales. And so we sort of really see that if you get to K of 1 and smaller is when you can begin to differentiate a lot of these models. And so really, we need measurements of the power at smaller scales to be able to differentiate these models. And they can also leave imprints that look like primordial, but are at late time. And so then just to conclude, I just want to talk. So the interacting dark sector models are sort of motivated targets for extensions of lambda CDM because they help alleviate some cosmological tensions and still provide good fits to the CMB and large scale structure. So we know that they're not ruled out. And so we hope that in the future with large scale structure data and CMB combined analysis, we can get, with measurements of the matter power spectrum at smaller scales, we can sort of distinguish between these different models. Yeah.
All right, I will start with a question. Could you go back one slide? This warm dark matter model, do you know what warm dark matter model that is that you're comparing to, just so that I get a sense of how these models compare?
I think this is about 10 keV. I just picked it because I wanted to keep the sort of IR suffix. So this is holding matter radiation equality fixed.
Okay.
Yeah.
Thanks. Other questions? Yeah.
Thanks for the nice talk. I'm wondering what redshift are you plotting this matter Pulse spectrum, and does that change over different redshifts?
Sorry, what redshift?
I mean, for this plot, for example, are you looking at the current universe?
This is, you mean what redshift is the matter power spectrum at?
Right, right.
This is
right.
today, yeah.
This is today.
Yeah.
And would that be different when you go to high redshifts?
Yeah, I mean, it would look slightly different. We just modeled it. I mean, we just plotted it today to compare to like observables to see, what you would look at. But yeah, at higher redshift. So we're looking at suppressions. So the cutoff scale in most of these correspond to sort of modes that enter around equality.
I see.
So if you could get, I mean, it depends on what sort of probes you could get at different redshifts of the matter power spectrum, but you could also distinguish there.
I see. Thanks.
Other questions? Yeah. Once again.
Okay, probably the Lyman alpha folks should chime in to be more quantitative, but I think this would motivate you to go to as high redshift as you could with Lyman alpha, because that would allow you to push to these small scales. I mean, that'd be the best that we could do, I think, at redshift 4 or 5. I'm looking to the person sitting right next to me right now.
Not many line of sights with quasars.
Sorry, we can't hear you.
Oh, I was just saying there's not many line of sights with quasars, so I don't know. Okay, that's a whole other.
The quasars aren't dense enough?
No, I mean,
Okay.
I would say, sure, someone else might want to pitch in, but
But these are, I mean, this huge suppression.
But some of these models
Yeah,
are already ruled out, right?
Yeah, I mean, so the interaction strength is like a free parameter. So I just
Sure.
put one plot here. Yeah.
Yeah.
We fit to, of course, the Lyman alpha data in the earlier talk she mentioned. So you get different interaction strengths. But yeah, I mean, for the weakly interacting case, you're looking at something like gamma over H will be like 10 to the negative 2. So these are pretty weak interactions.
Okay, one more question or? Okay, last talk. All right, patchy dark screening, John Milkwan.
Okay. Thanks, Risa. And since I'm the last speaker, I will thank all the organizers and all the locals for a nice workshop. So I'll be telling you about patchy dark screening. This is some series of work with these amazing young scientists and Dalila, Christina, and Fiona, and also people you probably already know. So we'll be telling you about a new type of secondary anisotropies. So as you heard from Salim's talk, secondary anisotropies are generated when CMB photons go through the large scale structure, getting perturbed by interactions, either gravitational or electromagnetic interactions that generate new anisotropies that we can observe. So mostly we have been using these secondary anisotropies to learn about the growth of structure, and from that learn about either known physics like gravity or unknown physics that we're trying to constrain. So here we'll be using them quite differently. We'll be looking at different tracers of structures, the galaxies we already observe, and use them as tracer to learn about new physics, especially those that can couple to photons. And for new physics, I'm mostly talking about light-dark sector, which includes axions and dark photons as two prime examples. And these are basically the particles that Peter talked about on Monday. So we'll see how we can use these secondary anisotropies to probe the parameter space above these red lines. The effect we are trying to look for are resonant conversions between the CMB photon to dark photon. So this is basically what we are doing all in the dark matter labs. We are doing the reverse process or like many of the lab experiments. But in cosmology, this is set up automatically for you when the universe actually scans the resonance by changing the density and the ionization fraction in the early universe. So, so in this plot, you see that from recombination all the way to today, you scan basically order magnitude, 6 to 8 order magnitude of plasma frequency of photon mass for which this conversion can happen at a different time. So there are a second scanner, which happens mostly at a late time after structural growth. This is basically a halo density profile. The orange is the electron density profile. And depending on your dark photon mass, you will be converting at the different locations inside the halo. So let's look at this a little bit more carefully. So here what happens is a CMB photon, which is coming from the left, going through the halo with electron densities. It will get to a point where the dark photon mass is equal to the plasma frequency, and the resonant conversion happens. And this resonant conversion is described by a conversion probability, which has a frequency dependence of 1 over omega for the dark photon. And it has a spatial dependence, which is basically showing you by this green circle. So with this conversion, you lose some photon, and that is described by optical depth, tau, which is absorption optical depth that has a frequency dependence. So let's look at the anisotropies this can generate. So you have some photon which goes to the halo. Some photon gets lost, so it leaves a cold spot. So here we are talking about conversion. So some photon gets lost, meaning that even if you start with something that is totally uniform at the last scattering surface, you generate anisotropy, which means that it is directly proportional to T-bar, which is 5 order magnitude bigger than the anisotropies. So when you have a lot of halos, then each of them cause some cold spots. So now now you have the primary CMB anisotropies, but also these dark screening anisotropies, which itself is a map. So we can separate these two anisotropy maps by using the frequency dependence of the optical depths, which means that we can use ILC methods that we heard about on Monday to separate the dark screening map from the CMB primaries. With these maps, we can do a lot of things. So the first thing we can do is just take the average. So, so this is what people have done before. Since you are removing photon in a frequency-dependent way, this is basically leading to a spectral distortion. But since we have done all the hard work to get the map, we can do something smarter. So we can compute all these correlation functions. And here I want to highlight again the T-bar dependence here, which if you are expert, you know, like the Thompson screening would scale as CLTT, while this thing is 10 order magnitude larger. So unfortunately, when we are in the business of looking for very, very tiny signal, we are not very happy when we see this epsilon to the 4 scaling, where epsilon is basically the small parameter coupling the standard model to the dark sector. We want to see something that scales better. So that's what we, that brings us to this estimator, which is basically a cross correlation of the dark screening map with the large scale structure surveys, which produce these maps of galaxies. So here it's a scale as epsilon squared. And generally, we expect there are a large class of these cross correlators between the maps that can be generated from BSM physics with the standard model tracers that generate them. So here we have a one with CMB and large scale structure. So I said a large class, and here is a second example. You can also look for CMB photons converting to axions. Here, the only difference is that the conversion has to happen in galactic B field. And it also generates screening of the temperature, but also since you're removing photons with polarization that are aligned with the galaxy B field, or like the B field of these other galaxies, not our galaxy, then like you can also generate some polarization signal in the CMB. So we forecasted the sensitivity of present and future experiments on these new anisotropies. So on the left, we have the dark photon, where we see that even with existing data, we can do order of magnitude better than existing constraint. While on the right for axion, like if we do work very hard, we can compete with the astrophysical constraint that mostly come from Ben Safdie's group here. So we did some analysis with Colin's group in Colombia, mostly led by Fiona, where basically what we did is we take the CMB measurements, we extract maps with a particular spectral energy distribution. So here, like for the dark photon 1 over omega, we generate these dark screening maps from the CMB measurement, and we cross-correlate with the NWISE galaxy sample, from which we can get the L-dependent of this cross-correlator. We compare with model predictions, and unfortunately, we didn't find anything, so we get a constraint. So as you see, it's roughly 30 times better than existing, even just with Planck cross NWISE. So in the future, we can expand the reach of these cross correlators. So going to the left, so this is in response to Simone's request. So if you want to go to the left, you want to use tracers, which has lower electron density. So when you want to go to the right, you want to go to higher redshift or like even denser regions inside the halo. And if you want to go do better, then like you want galaxy catalogs with more galaxies or CMB experiments with lower noise. This is how it scales. And we hope we can do better with the new generation of surveys. So this is just one example of these secondary anisotropies. We mostly talk about the CMB, but like we can use different things as the background photon. We can use different tracers. We can study different dark matter models. We can construct all kinds of these correlators and be sensitive to all kinds of new physics that couples to photons. That's it. Thank you.
All right. Questions? Let's do this one first just to save the running.
Yeah, I'm sorry. Thanks, Curly. The electron density, are you marginalizing over some shape of, some functional form for the electron density, or is it assumed like that you know that perfectly?
So for the electron densities,
yeah.
you mean? So like in the end, like we only need to know statistically what's the rough distribution of the densities. You don't need to know very precisely. So we just use the Battaglia profile.
You use what, sorry?
The Battaglia profile for electron
densities. I see, okay.
Yeah.
Okay, right. Yeah.
Hey, Curtis, thanks for the nice talk. A very random thought. Have you thought about like, because for FRB scientists, they are measuring the column electron density. And have you thought about like correlated this with what they already measured for all the FRB sources? Would that help your sensitivity?
So we want from Kendrick the electron density profile outside the virial radius. With those, we can get to lower masses.
Yeah. I see. So the integrated column density will not help you much.
Integrated column density won't help very much.
I see. Yeah. Okay, thanks. You kill my idea in a second.
Just following up on this slide. So how does it change with the average galaxy redshift?
So like higher redshift goes to the right for this plot, especially for the axion, it goes to the right. So if you want to probe like heavier masses, then you want to go to higher redshift. Yeah, we are doing like, so part of it is we want a higher redshift, and part of it I need to work harder. so that we actually populate the whole mass range. Yeah.
So where it says redshift here, does this mean just having galaxy redshifts, or does this mean?
Having tracers for galaxies at higher
Okay.
redshift,
Okay, got it.
or bubbles, or anything.
Great. Other questions? Okay, let's thank all of our speakers. We still have 15 minutes for discussion. So I hope you guys are thinking about what you want to discuss. Let me kick it off by just asking people, given what we heard in this session and thinking broadly about probes of the dark sector and dark matter, where does that push us in the space of a future spectroscopic survey? Is it obvious? Where are the trades, et cetera? Does anyone want to start that conversation? The speakers are welcome to chime in again as well. I'm going to give the room another minute before I say anything. Great.
So this is really a theorist bias, because we hear a lot of dark sector physics and warm dark matter, fuzzy dark matter, and maybe some simplified models. And it feels like we are mostly interested in those models that can give you near future signals. And we didn't really ask the question of whether this is theoretically well motivated, or how do we connect this or fit this into a broader picture that might solve other fundamental problems. So I'm really trying to just like asking like, what should be the way we do research? Should we just do whatever we want, whatever we are able to do, or we really think like we need our preference, we need our bias before we invest time or invest effort into this? We should think more carefully about the physics we're trying to test. It's very general, sorry.
Yeah, it's a good question. Does anyone want to comment on that? Yeah, Ethan, go ahead.
So from my perspective, I mean, I agree it's a good question. I think the point is that there are observables that give you a lot of fundamental physics for free. And whether or not that's a detection of fundamental physics, I think we want to know what the mass interactions and production mechanism of dark matter are. And if we can probe small scale power spectrum, we will learn those things regardless of whether or not that's theoretically motivated.
Yeah, Ethan, could I ask you to put up that figure with the power spectrum again, just because I think it's a good way to ground the discussion? And specifically, I want to push on the question of, I mean, Ethan talked about dwarf galaxies. We heard a little bit about Lyman alpha forest. Where are the places, right now, the best constraints, where that circle is, are coming very locally from dwarf galaxies in the Milky Way. We know that for dwarf galaxies, there's going to be some combination of, going a bit further out to pin some uncertainties down and trying to get as far down the mass function as we can. But there is a limit there. There are other ways to do this in the Milky Way, but I want to talk about the trade-offs between doing this in the Milky Way, going as far down as we can, potentially even to dark halos, versus going to high redshift. What are the differences in the physics we probe? What are the trade-offs in the systematics, et cetera? People are just tired, huh? Kyle, do you want to comment? Okay, great. Great.
I mean, I've actually wondered your question exactly, but maybe framed in other ways. So when we do this locally, it's not at all like a power spectrum measurement. It's like a halo counting measurement, right? And would that be, if we go to high redshift, is that the approach we take where it's counting galaxies, or do we actually literally compute a power spectrum as you go to those larger scale, those larger redshifts? And if it is the power spectrum, how do you actually resolve it with a lot of the, the general assumptions that we lose information at these scales due to all the galaxy physics? So my first question is, what's the actual measurement you're doing? And if it is a power spectrum, how are you not losing information?
You mean at high redshift?
I mean at high redshift. At low redshift, it's about halo counting.
Yeah.
So first question, are we halo
Yes.
counting at high redshift? Or are we doing a power spectrum at high
I
redshift?
think we're starting with the power spectrum, but I assume one could do other statistics, right? Satya, do you want to comment, or do you have any comments about Lyman alpha forest at these redshifts? I don't know.
Sorry, I
You
was
can-
scanning the room. I
Okay,
actually did
no,
not
that's
do-
fine. That's fine. Didn't mean to put you on the spot. Yeah.
Just a very minor comment for the local observation. I feel like, because as Kyle said, we're basically doing halo counting, then maybe disruption from the disk or just tidal forces will actually change the number of halos, which is like an extra ingredient from your primordial matter power spectrum, and that adds some complication.
Yeah, absolutely. I mean, Ethan and I are actively working on that right now. I agree that it's a key systematic that needs to be controlled. And some of those systematics are either non-existent at higher redshift or just very different at high redshift. Right. So I do think that even if you're probing the same scales, probing it at different redshifts is extremely useful. There's no question about that.
Okay, since people are tired, I'm going to keep talking. One thing I would like to see is more kind of end-to-end analyses of the same models across scales, because that's really where the signal is going to come from. Even if we detected something on small scales, I doubt that many people would believe it unless the same physics was also detected at larger scales. And that might be a milder suppression in that case. But that's an area that I don't see being really developed, is kind of unified inference across the full range of scales where we have data.
Yeah, strong agree to that point. Another question is just, I mean, with the range of models that we heard about today, so, we could take the simple warm dark matter version and its analogs. Many models map fairly cleanly onto warm dark matter. And in warm dark matter, it's relatively easy to understand. Like, you're probing a scale, you can easily understand what you're probing at redshift 4 versus redshift 0. Are there other models, including the things we heard about today, or anything that people are thinking about in the audience, where it's not that simple and there's a different calculation one wants to do about where the most relevant information is?
Another minor comment, if you look at the plot at the right corner, there are many models there. We don't talk about that today. And actually, if you simply rescale them, some of the model parameters, they will be moved to the left.
Yes.
And
Yes,
those are
absolutely.
naturally the models we also want to test, I think.
Yeah, totally agree with that. And I mean, I think the first half of your comment is also related to your previous comment that we're mostly talking about things that are measurable, about ways that we know of in the next decade,
Right.
say. But yes, most of those models could be moved to the left.
And then they are probable with different kinds of things, including, with high redshift galaxy surveys. So I think that's very worth sort of thinking about in detail and thinking about which systematics need to be understood and which models can be controlled. And like Ethan said, comparing different scales and different redshifts. I think that's a good point. Yeah.
I guess I have a challenge for the people who are doing simulations. So I think like one particular interesting case is the freezing candidate, where where you have a very, very light mediator. So in that case, you have basically like a plasma, and in various situations, you can drive different plasma instabilities. So what happens in those cases is, I think, like a very interesting, because like we have like a lot of experiments designed to look for these dark matter candidates and whether they are viable in the like astrophysics or galaxy context is interesting to know.
Yeah, that's great. Are there other model parameter spaces that people feel that the community should be thinking about a lot harder than we are, both in sort of simulation modeling and then how we probe them? Yeah.
We talk a lot about models. Might there also be options to do more model agnostic searches? We heard that the word simplified models was already floated, but I think more going in that direction, and rather than picking this kind of entire zoo of scenarios, trying to find where is there overlap in signatures, and then rather than drilling down and looking for the signatures separately for all these models, looking for common ones, constraining those, which then maps onto this entire classes. And on the other hand, if you find something, then that would be another way of then drilling down in those sectors. So I think that's also a bit of that's a charge for theorists to be creative in how to kind of rephrase parameter or model spaces.
Yeah, I think that's a great comment. And I think, in the simplest version, one can imagine just looking for a suppression or even an enhancement of the power spectrum on small scales at any redshift, and just trying to understand how well can we measure that, right? And then generically, one can map that to a wide range of actual physical models. So I do think that's useful. Give you this one.
Hi, as somebody who just does particle physics and doesn't know the astrophysics very well, I think it would be useful to also have what the bias can do, like have some kind of plot like this, where the new physics is bias, and just for me to see, if my new physics model is completely degenerate with the different kinds of bias, for example, in the effective theory of large scale structure, or the bias effective parameters, I think would just be a fun, informative plot, maybe.
Yeah, I think that's an interesting point. I think that some parts of parameter space lend themselves easily to that, and some less so when you're talking about, actually measuring the halos directly. But I think it's a good point and worth thinking through. Other things that people want to talk about in this space? Yeah.
So first, yeah, so to Ben's point, I mean, totally agree. I mean, to some extent, I mean, this ethos business was kind of meant to do that. And just kind of going back to this plot, I mean, this is like the abundance. Of course, there's also the some of the other dimension, like this the self interaction, or that they're kind of orthogonal, although related in any kind of theory parameter space. That maybe if you think about spectroscopy, which is supposed what this is about, it maybe is actually quite relevant because you're probing you want to probe the density. I wanted to go back to your first question because I guess I'm a little confused. So I understand the local probe, the things that you and Eaton and others are doing. I understand that kind of strong lensing, which you can probe at maybe a higher redshift. Now, the context of spec S5 and spectroscopy, so past K of 1 for the galaxy, I mean, there's not much you can do, right? So I think that's the case, right? Right? And then okay, the Lyman alpha, you can push that to some extent. I don't know exactly how far you can push it, but you can definitely go to higher redshift and do something interesting. But K of 1 and maybe K, right? But to your question, was there anything beyond that I'm missing, or
I'm on the same page with you.
Okay.
Trying to understand whether there were other ideas, and it does depend on the model that we're talking about, right?
Right.
I mean, not all models are this. Oh, sorry. Right. I mean, not all models are doing this suppression. There are other signatures, and we heard about some of them in today's session. And so in some of those, it may be that you don't need to go to smaller K.
I mean, can I just reverse sort of this argument? Because I think, I mean, for me, it feels kind of weird that we are talking about spectroscopic surveys, scales larger than K of 1, and then all the dark matter is, about K of 100. Because we're really missing, if we do that, that's great, but I think we're missing an opportunity because we can really predict the power spectrum, the bispectrum, the cross correlation from first principle without any uncertainty. Of course, we pay the price of the bias, but that's okay. That just means that if we have a detection, we can trust it, right? So I think, this pessimism that the bias is degenerate within physics, so it's, making impossible to look at various parts of parameter space, I think it's just too much pessimistic because in that part of the parameter space we have access to, if we find something, then, it's robust. I gave an example, right? 10 orders of magnitude of parameter space, which is, just open.
Right, but you're talking on the kind of the EFT kind of side. So K less than 1 or 0.3, right? So just to make sure I didn't say your comment, this is what you're talking about?
Yeah.
I mean, I totally agree. Yeah.
I mean, maybe right. There's things we can do in the deeply nonlinear regime, and there are things we can do at the K of 1 regime, and it's not right. So there is a question about whether large surveys at high redshift are going to be competitive with things that we can do in the deeply nonlinear regime, right? Yes, absolutely. No, absolutely. I'm not saying we shouldn't do both. I think we absolutely should.
Better say something smart now, right?
Yes.
So I mean, there is an intermediate regime related to this biasing, right? And so we can really go from lambda CDM, and knowing the Wimplet's MO, and then build the sort of EFT, kind of the large scale, sort of the model for that, right? With all the biases and so on. But we know that this is sort of a fluid, generic kind of model, and we know what sort of high level kind of physical assumptions go into it, like equivalence principle, right? Some sort of Galilean invariance and this sort of things, right? Scale separation, right? Single scale where gravity dominates, right? And then everything else you push to smaller scales. So you can use this, right, to build sort of models and kind of classify your sort of small scale physics or your particular sort of model in respect to these principles, right? Because those, if you just assume those, you're inevitably led to the sort of canonical, let's say, EFT model that we have, right? It's not really necessary to build, like, start from Lagrange and then build it, right? So in Emanuele's example, right, you could immediately say, right, okay, if I have 2 degrees of freedom, I don't have scale separation, right? I will end up with some sort of relative terms which will generate more bias and so on, right? So it's sort of possible to do these kind of argumentations in the mean steps, right?
Okay, I think we are out of time. Do we have a break now and then there's a? Okay, great. So we will come back at 4 o'clock.